Hey everyone, welcome back to the channel. This is part two of the video series where I'm attempting to explain every Sudoku technique. If you haven't seen part one, I'll leave a link to that in the description. I would definitely recommend watching it because we're building off a lot of the foundation that we covered in part one. A couple disclaimers before we get into it. First of all, the techniques we'll discuss in this part are a lot more complex than the techniques in part one. I promise there are simpler techniques down the line, but I wanted to organize these videos based on similarities in the underlying logic rather than just by increasing complexity. And I think the advanced group techniques we'll cover in this part are a really natural extension of the basic group techniques we covered at the end of the last part. Secondly, a lot of these techniques are very new to me. I didn't even find out about most of them until I did the research for this video. So if there are any inaccuracies that you notice, please feel free to let me know in the comments. But yeah, other than that, let's get into it. So at the end of the last part, we learned about naked groups and hidden groups, which are really powerful and relatively simple techniques that allow us to make a lot of eliminations for candidates on the grid. But one thing that we're going to find when we search for these groups is we're actually going to find a lot more instances where it looks like we're about to get a group, but then maybe we're just one candidate off. So let's take this grid, for example. This is just one of the puzzles within the Sudoku Coach campaign. But let's take a look at this row. So if you look at these three cells, we have 5, 8, 4, 5, 8. Looks like we're kind of starting to get a group, maybe a naked triple of 4, 5, and 8. And then we have this final cell 1, 4, 5, 8. And if it wasn't for that extra one, we would have a naked triple. That would allow us to make a lot of eliminations. We can get a 7 there. We could get a 1 here. But we're just one candidate off. And this, of course, goes for hidden groups as well. Let's take a look at this box right here. As you could see, we have 4, 6, and 7. It looks like they're confined to these three cells, which would make that a nice hidden triple. But what do you know? There's a 4 right there, making it almost a hidden triple, but not quite there. And we could even extend this to simple occurrences. All of these cells you see that only have two values in them, we call them bi-value cells. Um, we could consider those almost naked groups of one or naked singles. And whenever we have a candidate that can only be in two places, take this one, which can only be here or here, and this box, for example, that's called bilocal, but we can consider that almost a hidden group of one or a hidden single. So these kind of instances where you almost get a group can be pretty frustrating, and they don't really tell us any information on their own. But what we could do is we could actually combine a lot of these almost groups and find patterns that allow us to make certain deductions using some advanced logic. And that's what we're going to go over today. So let's go over the principle of why this works. So the extended subset principle, or ESP, is a foundational rule that underlies pretty much all the group techniques in Sudoku. And basically what the ESP says is that if you have a group of cells, the number of times the candidates in that group can be placed must be greater than or equal to the number of cells. And this actually makes a lot of sense when you think about it, because let's say if you have a group of 5 cells and the candidates composing those 5 cells can only be placed a total number of 4 times, then you're not going to be able to fill up all of your cells. So this would violate the ESP and it would be impossible in Sudoku. So let's take a look of an instance where something like that could occur. I have a grid here from Sudopedia. They have a really good article on the extended subset principle, so I'll put a link to that in the description. Make sure to check that out. But let's take a look at these cells highlighted in yellow. So you'll notice the candidates composing them are 4, 5, 7, and 8. And let's start with 4. There's 3 4s in this group, but you can see 2 of them share the same row, 2 of them share the same column. So we could really only place a maximum of 2 4s within this group of 4 cells. We could place a 4 here and we could place a 4 here. There's no way we could place 3 4s without them seeing each other. With 5s, there's 2 5s within this group of 4 cells, but they both share a row. So we could only place a 5 here or a 5 here. So we can only place 1 5 in these 4 cells. With 7s, there's 2 7s here and here. and they both share the same column, so we can only place a 7 once. And then with 8s, by a very similar logic, they both share the same column, so we can only place an 8 once. So if you're keeping track of that and counting them up, we have 2 4s, 1 5, 1 7, 1 8. That's 5 total placements across 4 cells. So that makes sense within the extended subset principle. But let's look at, if we were to place a 4 within this blue cell, let's look at what would happen to that group. A 4 here would eliminate all of the 4s within this group, and now we're only left with candidates 5, 7, and 8. And as we established, our 5 can only be placed once, our 7 can only be placed once, and our 8 can only be placed once. So that leaves 3 possible placements across a group of 4 cells, and that violates the extended subset principle. Therefore, we cannot place a 4 in this cell. So that's the elimination that we can make on this grid using ESP. Anyway, the extended subset principle basically is just a rule that prevents us from leaving a cell empty. And there's an interesting corollary to this rule that prevents us from filling a cell with multiple candidates, but we'll go over that a little bit later. So anyway, this is a nice rule to have, but it's really not that useful if we don't know what situations we can look for it. Because obviously we're not going to go through every single combination of cells in the entire grid to see if there's any contradictions. So let's go over a couple techniques that allow us that make use of the ESP. So the Sudoku is a technique that occurs when we have a lot of shared candidates between a box and a line that intersects that box. So here I have a grid from the Sudoku page on Sudoku, link in the description to that. And let's go ahead and take a look at this row 7 here. So if you take a look at these highlighted cells, we have a 4 5, a 3 5 9, and a 4 5 9. And then you'll notice that 4 5 9 and 3 5 9 intersects this box here. And within that box, we had the highlighted cells 4 5 9, 3 5 9, 3 9. So over these 4 cells, we have 4 candidates, right? And the thing that actually makes this Sudoku work is that we have these 2 cells in the intersection hold those 4 candidates. And then this cell that's only in the box and this cell that's only in the row are disjoint pairs of those 4 candidates. And what I mean by disjoint is that there is no overlap between the candidates. We have 3 4 5 9. This cell contains the 3 9, and this cell contains the 4 5. And if we apply ESP to this scenario, we'll actually find that each candidate can only be placed once in this group. So let's take 3, for example. Within this group of 4 cells, a 3 can only be placed here and here, and you'll notice those are in the same box, so we could really only place that 3 one time. And that goes for the 4, 5, and 9 as well, just because of the fact that these 2 cells are disjoint. So given that there are 4 cells and only 4 placements, that means that anything that eliminates a candidate from these placements ends up violating the ESP and therefore can be eliminated. So that leaves the 3 and 9. Anything that's a 3 and 9 in this box can be eliminated. There aren't any other 3s, but there are 2 9s in these 2 cells. So we could eliminate both of those. And anything that's a 4 5 in this row can be eliminated, which really is only the 4 in this cell. But as you can see, that's important because that leaves us with a naked single of a 1 in that cell. So that is the simplest occurrence of the Sudoku technique, where you have 4 cells. But there are a lot of situations where you have extra candidates that prevent us from getting that 4-cell Sudoku. However, there's a really neat rule that we could apply, where for every extra candidate we have, we just need to find an extra cell in order to make the Sudoku work. So I have another grid from Sudoku here, and let's go ahead and take a look at these cells highlighted in yellow in row 8. We have a 3 5, a 3 5 8, and a 5 7 8. So if we just had a cell in this box that was a 7 8, that would make a great 4-cell Sudoku, because then these would be disjoint pairs, and that would cover the 4 candidates 3 5 7 and 8. But the thing is, we don't have a cell with 7 and 8 in this box. What we do have, however, is we have a cell that has 7 9 and a cell that has 8 9. So those 2 cells together can fulfill that same role. And because of that, we can now eliminate 7, 8, and 9 from this box, and we could eliminate 3 and 5 from this row. We could use that same logic for extra cells in the intersection as well. Let's say if in this cell, instead of it just being 5, 7, 8, it was 4, 5, 7, 8, well, all we would have to do is just add another cell in the intersection, and there's a perfect one right here of 4, 7, 8. So if we added this into our Sudoku, then now we, instead of just eliminating 7, 8, and 9 in this box, we can now eliminate 4, 7, 8, and 9 in this box. And instead of just eliminating 3 and 5 in this row, we can now eliminate 3, 4, and 5 in this row. So every extra cell or every extra candidate, you just need an extra cell. And if that extra cell happens to be in the intersection, then you could eliminate from both the box and the line. And yeah, that is the Sudoku. So the next technique we're going to go over basically generalizes the Sudoku, but does so using a very different approach. And that technique is called almost locked sets, or ALS. So an almost locked set is basically an almost naked group. It's when you have n cells with n plus 1 candidates. And all Sudokus are essentially just two almost locked sets. So you could actually see that here with this Sudoku we just went over. If we take these 4 cells, we'll notice they have 5 candidates across them. And if we take these 2 cells, we'll notice they have 3 candidates across them. So all Sudokus are basically just two almost locked sets, one of them being on the line and one of them being in the box. Now, the thing that makes this even more interesting, though, is that these almost locked sets are linked in the fact that they have what's called a restricted common candidate, or an RCC. And I know I'm just throwing a whole bunch of acronyms out, but bear with me here. An RCC is basically a candidate that is shared across both ALS, but every instance of the RCC in one ALS sees every other instance of the RCC in the other ALS. So in this Sudoku, we actually have 2 RCCs. One of those is the 7. You'll notice that within this ALS, the only place the 7 appears is here. But this 7 sees every other instance of the 7 in our other ALS right here. And our other RCC is the 8, which, by the same logic, this 8 in our one ALS sees every instance of this 8 in our other ALS. The thing that makes RCCs important is that they can only be placed in either or ALS, whereas every other candidate could technically be placed in both ALS. So effectively, what this means is if we were to combine the pair of ALS, regular candidates would have 2 possible placements, whereas RCCs would only have 1 possible placement. So when we have an RCC, this effectively lowers the number of candidates across the pair by 1. And when we have 2 RCCs, what we're doing is we're taking 2 n plus 1 candidates and reducing that to essentially a pair of n candidates, making one large naked group. And this ends up resulting in the exact same eliminations that we can make using a Sudoku logic. However, almost locked sets are actually more flexible than Sudoku because they can be used in instances where you don't have an intersection between a box and a line. Take, for example, this grid, which is from the almost locked sets page on the Sudoku wiki. You can see here that we have 2 ALS, one of them being highlighted in these blue cells and one being highlighted in these yellow cells. And you could also see that we have 2 RCCs. The only 2 in the yellow ALS sees the only 2 in the blue one, and the only 4 in the yellow ALS sees the only 4 in the blue one. So this makes them doubly linked, and that means we could eliminate any candidate that would empty out a non-RCC from one of the ALS. So that means we could eliminate all of the ones in this box, and for that matter, we could actually eliminate all the other ones from this row as well, considering the yellow ALS also is entirely in row 4. And then we could eliminate all the 7s and 9s from this row 2 as well, which it doesn't actually appear that there are any. And then on top of that, we could also eliminate any candidate that would empty out all RCCs between these 2 ALS. So that's going to include all the 2s in this row and all the 4s in this row. So that is basically the doubly linked ALS. So we've seen that ALS with two RCCs behave pretty similarly to naked groups, where we could essentially eliminate any candidates outside the ALS, provided that those candidates aren't one of the two RCCs. However, what happens when we only have one RCC? Well, this is where we have to make use of a rule called the ALS-XZ rule. And I'll go ahead and demonstrate an example of that here with this grid. This is also from the Almost Locked Sets page on the Sudoku wiki. But as you can see, we have two ALS here, one highlighted in yellow, one highlighted in blue. And you could see we really only have one RCC, and that's the 6 right here. The only instance of the 6 in this yellow RCC sees the only instance of the 6 in the blue in the blue ALS. We'll call that 6 or one RCC. We'll call that X. So this situation basically creates one set which has n plus 1 candidates and one set which has n candidates, depending on which set the RCC is in. We don't know which one's n plus 1 candidates. We don't know which one's n candidates. However, if we were to empty out a candidate from both sets at the same time, we would be creating a situation where we have one set of n candidates and one set of n minus 1 candidates. And that's impossible because we can't have n minus 1 candidates across n cells. But the only way to empty a candidate out from both sides at the same time is if both ALS share another candidate. And that's the Z part of our XZ rule. So the ALS-XZ only works if we have one RCC and one other shared candidate, which is not an RCC. So this actually works in this case because we have an 8 in both sets, and this 8 is not an RCC. For example, this instance of the 8 does not see this instance of the 8, so that would make it not an RCC. But it is a shared candidate. Any instance that eliminates this shared candidate from both sets is impossible. So the only way we could do that is if we were to place an 8 here. And if we did that, we would be reducing the number of candidates in both sets by 1, which is impossible because there already is an RCC. So what we could do is we could actually remove the 8 from this cell. And that is the ALS-XZ rule. So the ALS-XY-Wing basically extends our ALS-XZ rule into a triplet of ALS. And we could see that here. This is a grid from the Sudoku page on Almost Locked Sets. We can see we have 3 ALS, so that's 3 sets of n plus 1 candidates, or 3n plus 3 candidates. But as you can see, our blue ALS has an RCC of 9 with our yellow ALS, and our yellow ALS has an RCC of 7 with our green ALS. So that RCC of 9 brings it down to 3n plus 2 candidates, and that RCC of 7 then brings it down again to 3n plus 1 candidates. Our green ALS does not have an RCC with our blue ALS, but it does have a shared candidate of a 3. So there's only one cell that actually sees all instances of this 3, and that is this cell right here. So essentially what we could say is that if there was a 3 in this cell, we would be reducing the number of candidates by 1 in both this blue ALS and this green ALS at the same time. So that would bring us down from 3n plus 1 to 3n minus 1. And that would be impossible because then we wouldn't have enough candidates to cover all 3 of those sets. So we know a 3 can't be here. And that's essentially the analog of the ALS-XZ rule, but applied to a triplet instead of a pair. It's also important to note that if this 3 was an RCC, which we could actually do pretty easily by removing 3 as a candidate here, if there was an RCC between the green ALS and the blue ALS, that would essentially mean that each of these ALS would be doubly linked, and that unlocks a whole ton of eliminations. That allows us to eliminate 2 and 8 in this column. It allows us to eliminate 1 and 8 in this row, and allows us to eliminate 6, 7, and 8 in this row. So that is how we would extend these ALS techniques into a triplet. Subset exclusion is a technique where you test out every combination of candidates across a group of cells, and you can invalidate any combinations that empty out a cell that the group mutually sees. So invalidating any specific combination of candidates isn't going to give you a whole ton of information, but where subset exclusion becomes really powerful is when you're able to invalidate a set of combinations that all involve the same candidate, and therefore you can invalidate the candidate itself. So let's take a look at an example of where we can actually apply subset exclusion. This is a grid from Sudopedia, and this is actually the simplest case of subset exclusion called aligned pair exclusion. It's basically when we have a group of two cells that share a box and a line. So these are these cells highlighted in yellow. And these yellow cells can mutually see all of these blue cells. So let's go and test out the combinations of candidates in these yellow cells and see if any of those combinations empty out one of these blue cells. So first we have a 4. Let's say we have a 4 in this yellow cell and a 1 in this other yellow cell. Well, none of the blue cells consist of a 1 and 4, so that isn't really going to tell us anything. 4 and 2 also doesn't tell us anything, and 4 and 5 also doesn't tell us anything. So it looks like all of these combinations of 4 and 1, 2, and 5 in the other cell are valid. But let's take a look at if we had a 9 in this top cell. 9 and 1 would empty out this cell right here, which makes 9 and 1 an invalid combination. 9 and 2 would empty out this cell, and 9 and 5 would empty out this cell. So we notice every single combination that involves a 9 in this cell empties out some other cell, which would be an invalid state. Therefore, we could eliminate 9 as a candidate, and that means this number must be a 4 right here. So as a side note, one thing I noticed with this grid is you could actually make the same deduction of eliminating the 9 in the cell using the ALS-XZ rule. And there'll be a lot of situations with these grids where you can make the same deduction using a different technique. So if you want to have some more practice with any of these techniques, I would recommend going back through the video, looking at each grid, and seeing how many of the techniques we discuss actually apply. Anyway, back to subset exclusion. There are situations where you can apply subset exclusion where the groups you're testing don't necessarily share a line or a box. Here's another grid from Sudopedia where our yellow cells are actually in different boxes and different lines, but they still mutually see all of these blue cells. So we can apply the same thing where we test out every combination of candidates between these yellow cells, but I'm not going to do every single combination because that would take a little bit too long. So let's go ahead and just focus on combinations where this cell is a 7. Spoiler alert, we are going to be able to make a deduction where we could eliminate the 7, but let me go ahead and show you why. If this cell is a 7, first of all, this cell couldn't be a 7 because then they would be in the same box and that would be invalid. But if this cell was a 7 and this cell was a 5, then this cell could either be a 4 or 6. If this combination is 5, 7, 4, well, you'll notice this cell right here is also 5, 7, 4, and these three cells mutually see this cell. That would empty it out and be invalid. If instead we had 5, 7, 6, this cell also shares those exact same candidates, and that would be left empty. So any situation where this cell is a 7 is invalid. Therefore, we can go ahead and eliminate the 7 as a candidate from this cell. Anyway, yeah, that is subset exclusion. The death blossom basically combines subset counting and almost locked sets, and by doing so, essentially generalizes both techniques. The difference is that instead of finding combinations of candidates that empty out a cell entirely, death blossom is all about finding combinations of restricted common candidates, those again being candidates that see all instances of a candidate in an ALS. And it's focused in finding combinations of those RCCs that reduce the size of an ALS by 2. So here we have a grid from the Sudoku wiki on the Death Blossom page. And we can kind of see the basic structure of a Death Blossom. So it essentially consists of a number of ALS. In this case, it is 2. We have a yellow one and a blue one. And these ALS are called petals, and all the petals are connected by what's called a stem cell. And that's this green cell right here. And your stem cell must be entirely composed of restricted common candidates, RCCs. And so what you could do with the stem cell is you could find combinations of that cell and another cell that contains an RCC for both sets at the same time. So if you know that your stem cell must contain one RCC and you find another cell that contains an RCC for 2 sets at the same time, you know that you're reducing the size of one of your ALS by 2, therefore invalidating it. So the only situation which we could see with this specific example is this 7 in this cell. You'll notice that this cell sees both of the ALS entirely, and these ALS share the candidate of 7. So if a 7 was to be placed here, it would reduce the size of both ALS by 1. And then, of course, since this stem cell is composed of RCCs, no matter what we put in it, it will reduce the size of one of those ALS by an additional 1, therefore making it too small and emptying it out. So this specific example is actually identical to just doing an ALS-XY-Wing. But the main difference between the death blossom and the ALS-XY-Wing is your stem cell does not need to be an ALS. In this example, it is because it only has 2 candidates in a cell. But we have another example here where we have a whole ton of candidates in our stem cell, 1, 4, 5, 8, and 9. And you could check each of these individually, but each of these are actually RCCs with one of our 2 ALS here. And with this specific instance of the death blossom, again, 7 is our elimination candidate because you could see that both of these ALS share a 7, and this cell sees all instances of a 7. So we can go ahead and eliminate the 7 there. So yeah, that is the death blossom. There are also cases where you could have more than 2 petals, so you could have multiple different ALS. As long as your stem cell kind of connects all the petals together and it is composed of restricted common candidates across the ALS. There should also be instances where you could have combinations of multiple stem cells or at least multiple cells containing RCCs, but I have not seen any examples of that. So if y'all run into any examples, please send them my way. I'd love to do a more in-depth video on this technique because I can't really do it justice in just a couple minutes. But that will be all for today. So you may notice that all the techniques we've covered so far have made use of the extended subset principle to ensure that none of our groups are underpacked and ultimately none of our cells are left empty. But we could actually approach this from a different perspective because every state where a cell is left empty creates a corresponding cell that's left overpacked, forced to carry multiple candidates at the same time, which is equally invalid. So it's helpful to devise kind of an alternate statement of our extended subset principle that rules out any invalid states where a cell is left overpacked. And one way to do this would be by stating that for any group of digits associated with the house, the number of cells covering that group of digits must be greater than or equal to the number of digits. And this is essentially just a rule that prevents us from forcing multiple different digits into the same cell. I haven't seen it explicitly stated anywhere, but this kind of naturally falls out of approaching the extended subset principle, but focusing on the digits first instead of the cells. And this also enables us to use a few additional techniques, notably almost hidden sets, or AHS, which are essentially the analog of almost locked sets, but for hidden groups instead of naked groups. Anyway, let's talk about a couple scenarios where we could apply this alternate perspective on the ESP. Almost hidden sets are when we have n candidates that are spread across n plus 1 possible placements. If you remember back to the intro to this part, I mentioned when you have a nearly hidden group, that's basically what an almost hidden set is. And for some reason or another, almost hidden sets aren't talked about nearly as frequently as almost locked sets. Frankly, I wasn't even able to find a good example of a grid to kind of demonstrate almost hidden sets. So I just kind of made this partial grid myself. Sorry if it's a little bit janky. If you find a good example of an AHS, be sure to send it my way, but this will have to do for now. So as you can see in this grid, I have full candidate notation with all the candidates in the center of the cell, and then I have our almost hidden candidates kind of out towards the edges. So you can see we have 2 almost hidden sets. One is highlighted in yellow. That is our candidates 1 and 2, which are placed across 3 cells in this box. You'll notice if we highlight 1 and 2, these are the only 3 cells which they're present in this top left box. And then our other almost hidden set is our candidates 3 and 4, which are 2 candidates placed across these 3 blue cells in this line. And as you can see, those are the only spots along this line where 3 and 4 are present. So one thing you'll notice is that 2 of these cells are actually overlapping between the 2 AHS. And that's really how we link together AHS. Unlike with ALS, where we have restricted common candidates, with AHS, we basically use overlapping cells. And it makes a lot of sense because the whole thing with almost hidden sets is that you have one extra cell placement. So if two AHS are competing for the same cell, you're effectively reducing the total number of cells by one. So if they both have one extra cell and you're knocking off two, you're basically forming them into one big hidden group. And we could actually verify this with our ESP that we just talked about. Notice how we have four candidates, one, two, three, and four, and they're across four cells. So if we were to place any other candidate in one of these cells, we would be limiting four candidates to three cells, and that would result in overpacking, therefore violating our ESP and bringing us to an invalid state. So what this means is that any candidate that is not one of these hidden candidates can be eliminated from the cell. So in this one, we could eliminate everything that's not a 1 and a 2. In this one, we can eliminate everything that's not a 3 or a 4. And in these overlapping cells, we could eliminate anything that's not a 1, 2, 3, or 4. So that's the simplest case of an AHS pair. But we could also get slightly more complicated cases where we have candidates that are shared between two AHS. So here's another case where we have an AHS with three candidates spread across four cells. We have one in yellow, that's 1, 2, and 3 spread across these four cells in the box. And then we have 3, 4, and 5 spread across these four cells on a line. And again, there are two overlaps, but you'll notice both of these AHS share the candidate of 3. So if we really look, it looks like we have 6 cells and only 5 candidates, which seems like we have a lot of leeway to even remove one of the cells and we should still be good. And that would be the case if we remove this cell because it doesn't share that common candidate. But if we remove this cell with the common candidate of 3, that means that we'll have this set where we have 1, 2, and 3 limited to 3 cells. And then we'll have this set where we have 3, 4, and 5 limited to these cells. And a 3 can't be here. So both of them would be fighting over this cell. And there isn't a candidate that could kind of resolve that fight and satisfy both of the AHS. So what this means is that whenever you have an AHS with a common candidate between them, any overlapping cell with that common candidate, you could eliminate anything that does not participate in either AHS. So in this cell, we could eliminate anything that's not a 1, 2, 3, 4, or 5. So another interesting scenario with AHS is when you actually have 3 overlapping cells. And now at face value, this seems like kind of a contradiction, right? An AHS only has 1 extra cell as leeway. So it seems like an AHS pair should only have 2 additional cells. Therefore, 3 overlaps seems like you're kind of removing an extra cell and over-constraining your set. However, this can actually work when you have a shared candidate between the two AHS. And in this example, we have 3 candidates across 4 cells in both the yellow and the blue AHS. And you'll notice we actually have a 3 is a shared candidate in both AHS. So in order to kind of satisfy this contradiction where we have 3 overlapping cells, we must have a shared candidate in one of those overlaps that could kind of satisfy both cells at the same time. So what we could do here is we could actually limit our shared candidate to one of those 3 overlaps. And then on top of that, we can get rid of any non-hidden candidate in any of these cells in the set. So that's kind of our third major scenario where AHS pairs play a role. So to succinctly restate those 3 rules, first one for an AHS pair is if we have 2 overlapping cells with no shared candidates, we could eliminate any non-hidden candidates from both set. If we have 2 overlapping cells and one of those overlaps has a shared candidate, we could eliminate all non-hidden candidates from that overlapping cell with the shared candidate. And then finally, if we have 3 overlapping cells, we must have a shared candidate in one of those 3 overlapping cells. And in addition to that, we can eliminate all non-hidden candidates from everywhere else in the set. So yeah, that is almost hidden pairs. So the last technique we'll cover in this part allows us to extend our AHS pair rules into groups of 3 AHS or more. So we actually have an example of that here. And you'll notice, since we've already seen what our AHS looks like with full candidate notation, I decided to clean up the grid a little bit and only show the hidden candidates, just so it's a little bit easier to see what's going on. Anyway, we have three AHS in this grid. We have a yellow one, which has our candidates 1 and 2 in these three positions in this top left box. We have our blue AHS, which has our candidates 3 and 4 in these three positions in column 3. And then finally, we have our green AHS, which has our candidates 5 and 6 in these three positions in row 1. So you'll notice each of these AHS has two overlaps. And if we apply our ESP overpacking rule, we could see that we have 6 total cells and 6 total candidates, which means if we were to place one of the non-hidden candidates in one of these cells, then we would violate our overpacking rule and create an invalid state. So what this essentially means is that we could eliminate any non-hidden candidates from any of these cells. So that's kind of our doubly linked AHS rule, but our other rules still apply as well. So if, for example, we were to have a shared candidate between two of these AHS in one of the overlapping cells, then we could only do eliminations from that overlapping cell, unless, of course, if we were to have a third overlapping cell for one of the AHS. And then our large set would once again become locked. And additionally, we could restrict our overlapping candidate or our shared candidate into one of those overlapping cells. So the rules basically can be extended pretty easily from a pair of 2 AHS to a group of 3 AHS. And we could see there's even an example here of a group of 4 AHS. We have our yellow AHS, which is just a bilocal candidate of 1. So 1 is spread across these 2 cells in this column. And then 2 is our blue AHS, and that is across these 2 cells in the row. 3, our green AHS, is spread across these 2 cells in this column 7. And then finally 4, our red AHS, is spread across these 2 cells in our row 7. So this, again, each of these AHS has 2 overlaps. We have 4 candidates across 4 cells, which means this essentially becomes locked, and we can eliminate any non-hidden candidates in one of these cells. I can't think of exactly what an AHS quintuplet or a sextuplet would look like, but the rules should still apply as we go into even larger groups. But anyway, that was pretty much all the rules I was able to find for AHS, but given how sparse the conversation is right now, I'm sure there's more out there to be discovered. Anyway, with that, we have finished the advanced group techniques video. If you enjoyed, if you learned something, make sure to leave a like. We will be continuing the series. The next part is going to go over fish techniques. That's X-Wing, swordfish, and the like. If that's something that sounds interesting, make sure to subscribe so you can stay tuned. And in the meantime, get some practice with some of these techniques. And thanks for watching.